658 lecture 54. So yesterday we saw how one might be able to derive the transfer function of the continuous time loop filter, which will result in a desired noise transfer function. Okay, and so if one considered the SIF loop filter, and I will take a third order example. The quantizer, blah blah. All right. Okay, we have found K1 from yesterday's discussion. We should be able to find K1, K2, K3 that result in a desired NTF. Once this is done, the thing is to build a macro model either in Simulink or in MATLAB and simulate the differential equations, right? So please note this is like a mixed system. It's continuous time in some part and discrete time in other parts. Okay, so to that extent, the simulation is will take a long time, especially when you put transistor level models for the loop filter as well as the quantizer. You've already seen how painful it is to simulate. You've done a 4-bit flash, correct, in your assignments, so you know how long it took, and for a 4-bit flash you don't need to, you can run only a 64-point FFT or something and you'll still be able to see clean results. Whereas in a delta sigma we said that if you run the number of bins you require in the signal band should be substantial. It should be at least if you use the Hanning window, the signal bin itself will the signal itself will leak to 3 bins. So if you want this to be at least 20% of the total signal band, then you need to have at least. This is also broken, so I'll just get rid of it. So you need at least about 20-25 bins to make a reasonable assessment of in-band SNR, in which case what happens, what you will need is to run simulation for a much longer time, right? So the FFT that you take, the FFT record length that you take must be a substantial number, alright, which means that the flash converter, this flash which has got a bazillion transistors must be run for a long time. And even though the input signal is varying with a very low frequency, that doesn't matter because the flash is sampling at every clock edge, right? And you know that every time you have, when you have sharp edges in a simulator, simulation time will increase because at the edges the derivatives are very high. So the simulator will go very slowly to make sure that it is giving you the correct answer. Okay, or at least you're supposed to set the simulation tolerances so that is true. Does it make sense? So the simulation will take a long time. There's no running away from it. Alright. So for example, if you put in a sine wave at the maximum stable amplitude, then what happens? There will be some waveform here. Okay, there will be some waveform here, something here, and something here. So what do you think, well, this is all in theory. In practice, what do you think happens? Any real integrator built with, op amps and stuff, is there a limit to how large the output voltage can go? Finally, you're going to design an op amp, right? And the output swings of an op amp are determined by the supply voltage and how much VGS minus VT you have for the top device and for the bottom device inside the op amp and so on. So the bottom line is that the output swing, the peak swing at the output of each integrator cannot go to arbitrarily large values, okay, in practice, because they have to be limited by the supply. They are limited by the supply, and in and you know, the operation of the modulator is already complicated enough without having to risk figuring out what will happen to the modulator if one of these integrators saturates. There is already saturation in the quantizer. Okay, so if the integrators saturate, you know, you at least, what you say is you don't know what could happen. Okay, so the best thing to do is make sure. One solution is to, you know, beat your head and figure out what happens when the integrators saturate and all that. Engineering way of doing it is to make sure that the integrators don't saturate in the first place, so that this model is valid for all inputs, okay, within the maximum stable amplitude. All right. Now, what can you say about the signal here? If this has an amplitude A, what can you say about the signal at this point, that is Y? Huh? No, think carefully. Okay, how will you model the quantizer? Additive noise. So what should Y be? Huh? Yeah, and what is V? Yeah. Huh? So V is nothing but A, the input plus shape quantization noise. Okay. So this signal Y of n, it's a discrete time signal. It will be the sampled version of the input plus, see, the negative feedback loop is going to make the signal component of this equal to the input. Alright. And on top of the signal component, there is going to be some shape quantization noise riding. So if you look at the waveform here, it will be signal plus shape quantization noise. It's NTF of Z minus 1 actually. Alright. So that basically means that what would be the signal here?
So the signal here is getting almost
Where?
when you subtract the signal.
Correct. So what is the signal here? What the question is raising is, if this is input almost equal to the input plus shape quantization noise, okay, what should the signal going in? This is input plus shape noise. All right. So when you subtract the two, what goes into the loop is shape noise. Okay. But if you just put in noise, you can't expect magically signal to develop here. So how is that happening? Please note that this is approximately equal to the input. Okay, it's actually STF into the input. Alright, and the STF is very, very close to being 1. So for all practical purposes, you can say what is going into the loop filter is shape noise. However, there is a very, very small input component to it. And that small component, please note, is going through the gain of 3 integrators. Alright. So that is getting amplified to A at the end of the loop. You understand? Please note that the loop filter has got very high gain at low frequencies and the gain keeps falling off. So a very small signal component is enough to generate a finite amplitude output at Y.
So but the small signal component also should have more amplitude than the shape noise.
No, why? Please note that the gain of the loop filter at low frequencies is virtually infinity. Correct? So as the gain becomes infinity, it requires an infinite stimuli.
More than the in-band quantity.
It should be more than the in-band quantization noise. Yes, definitely. Okay. All right. So most of this signal here is shape noise, and shape noise, as we know, is got mostly high frequency components. Okay. All right. So this signal here will basically have an amplitude will be of amplitude A plus some shape noise riding over it, and the variance of the shape noise you can figure out by you know the NTF, so you can go and figure it out. All right. So what if, so let's approximately say that this amplitude is A plus a few LSB, correct? Because the stuff will be jumping around the input by a few LSB. So what can you say about the output of this integrator? Is the diagram too confusing or what? See, let me redraw the cascade of integrators in this fashion. Perhaps that will help you. This is, what is this? This is y, alright. So this is getting sampled and then quantized and then getting fed back to getting fed back here. This is u, alright. So this we know is the amplitude of this is A plus a few LSB. Why is it A plus few LSB, Subrato? What about you, Siva? Yeah, so what? Yeah, so what?
Adding actually.
Pardon? So what? Why should it be A plus a few LSB? Okay, why this is a sine wave of amplitude A is because this is a sine wave of amplitude A. The signal transfer function is 1 almost, which means that the signal component here must be a sinusoid of amplitude A. Is that clear to everybody? Okay. And not only that, we know that this quantization noise is going through the loop, alright, and this output is nothing but, this is V, right. So this output will be, I mean Y will nothing be but will be nothing but the signal component plus some shape quantization noise. In fact, we have seen that the transfer function of the quantization noise from here, this is where E of n is adding, alright, that is nothing but the transfer function to y is nothing but NTF of z minus 1, alright. So it's taking quantization noise and filtering it through with the filter of NTF z minus 1, alright. So the signal component there will be a sine wave of amplitude A, and on top of it there will be a quantization noise riding, okay, alright. Now let's think carefully. If this is nothing but a summer, okay. So what is the signal component here? The low frequency component is a sinusoid of value A, amplitude A. So where do you think most of the the signal component of the sum has an amplitude A, and that must be coming from the signal components through this branch K1, through branch K2, and through branch K3. So what do you think is the which do you think is the most dominant source of the signal component? K3. Why? There are 3 integrators, so the gain is the largest in the third case. So most of this low frequency component will be coming through. Okay, that makes sense. All right, a little bit of the low frequency component will be coming through the path K2, and an even smaller bit will be coming through K1. All right, and of course, the quantization noise, is, you can think of it as getting filtered through 3 integrators here. So the output at the third integrator will predominantly consist of the input signal plus quantization noise, but which has been filtered through 3 integrators. On the other hand, this guy will consist of a smaller portion of the signal plus quantization noise, which has been filtered to a smaller extent. So the jagged edges in this output will be higher. Okay. This of course has got the smallest signal frequency component. All right, and the quantization noise being integrated just once. So you will find that the jagged edges, or the high frequency component of this integrated output is the largest. Is that clear? All right. But at this point, there is nothing you can say about what the maximum will be here, and here. The maximum amplitude at the outputs of each of these 3 integrators at this point is still unknown. Okay. You can perhaps compute it given the input and all this other stuff. But the easiest way of finding out what the maxima at the outputs of each of these integrators is through simulation. Correct? All right. So, and why are we interested in figuring out the maxima at the outputs of each of these integrators? You want to make sure that the outputs don't go too high. Otherwise, in practice, they will saturate the integrator. Does it make sense? All right. So let me call these state variables say x1, x2 and x3. So you can run simulations and find the maxima of x1, x2 and x3. All right, and they will come out to be some numbers. So you want to make sure that these maxima are all below a certain limit, correct, depending on the swing of your integrators. Does this make sense? All right. So in other words, let's say x1 max is for argument's sake 10 from simulation, x2 max is 5, and let's say x3 max will be some a by let me say it is 7. I'm just taking some random numbers. Nothing sacred about these numbers. All right. In other words, the peak outputs at each of these integrators are different and are found from simulation. No. See, this is the. Please note that the outputs of each integrator consist of both noise and signal. It is true that the output of x1 or the first integrator has got the smallest signal component, but it has got the largest noise component.
You're not using the single bit ADC, then the LSP is small enough, but you can assume that the noise introduced is smaller than the signal. So you can assume that the maximum amplitude at the output of first integrator is smaller than the.
Well, it's not okay. For sure, I can show you cases where that's not possible. Okay. So what happens if the input signal amplitude is very, very small? Then you will end up with, the outputs of x3 will be very small, but x1 and x2 will be larger, right? So
we are not bothered about small inputs because we are trying to find out whether the op-amps are saturating when you give the MSA.
Correct. So can you comment on the maximum at the output of the first integrator as a function of signal amplitude? No. The maximum at the output of the first integrator, do you think it varies with signal amplitude? Please note that, as you all said, the output of the first integrator has got the smallest signal component. Correct? So if the signal amplitude varies a little bit, the output maximum of the first integrator will be quite independent of the input signal amplitude. Correct? Whereas the second integrator will vary slightly, whereas the third integrator will vary a lot with signal amplitude, because the output of the third integrator is what is providing the signal component of y in the first place. Does it make sense? So all these maxima will be weak functions of the, x1 and x2 in this particular example will be weak functions of the input amplitude. x3 will be a strong function of the input amplitude. So that's why I've chosen to excite the modulator with the largest possible sine wave that we plan to put into the modulator. Does it make sense? All right. No, for instance, okay, if this was say 10 by s and this was k1 by 10. All right. So it's possible to have any number of loop filters which have the same transfer function, right? So and even though you have a multi-bit quantizer, the maxima also depends on the noise transfer function. It's not just simply the LSB error that you add, but this goes through the loop and gets amplified. Okay, so the bottom line is that the outputs of maxima of the three integrators, can be figured out using simulation. Okay, if not anything else. In principle, it should be possible to go and do the math also, but I think it's not worth it. You just use simulation and find out what the maximum. What is the job? What is the next job? Once you find the maximum, what should you do? Let's say I want to limit all my state variables to be less than or equal to, I don't know, let me take some arbitrary number, 5. What would I do? So I want the maximum of state variable x1 to be less than or equal to, Sandeep, what? Wake up. It's there on the the maxima were 10, 5 and 7, and I want the peak values of all the state variables to be limited to 5 in the worst case. Okay, so I want to make sure that the x1 doesn't go beyond 5. All right. So what would you want to do? If I want to reduce the signal amplitude here by a factor of 2, x max 1 was 10. I want to make it 5. So if I want to reduce the signal amplitude here by a factor of 2, what should I do to the gain of this block? I should multiply it by half. Correct? Okay, so let me do that. So I will multiply this by a factor of what was originally 1 over s. I will make it 1 over 2s. Yes? Okay, but now if I just made this 1 over 2s, what will happen to the loop filter transfer function? The loop filter transfer function is clearly changed, because we wanted earlier, you wanted k3 by s cube, but you're getting only 1/2 of k3 by s cube. Correct? And if the continuous time loop filter changes, the sampled version changes, which means that the noise transfer function changes. I do not want to change the noise transfer function, but I want to scale down the state variable. So if I multiply this by a factor of 1/2, what all should I do? So everything that is dependent on x1 should get multiplied by a factor 2. So in other words, I should replace this by 2k1 and 2 by s. Okay? Does it make sense? So now this represents, so can you now comment after I did this, what will be x1 max now? 5. What will x2 max be? 5, because I have not done anything to x2. Alright? And what will happen to x3? It will remain 7. Because, see, these guys don't know, for instance, the third integrator here doesn't know that this gain has changed, because this gain has also changed. You understand? Earlier, the signal coming here was the quantization noise integrated twice. Even now, it is the same thing. So, the peak here cannot change. Is that clear? Alright. The next thing to do is to look at x2. But x2 max is 5 already. So, I don't need to do anything to. The third culprit is x3. Alright. x3 max is 7, but I want to make it 5. So what will I do? I multiply it by what else should I just multiply k3 by alright, and now the state variables are all the peaks of all these integrators are have all the desired maximum, which in this case I have chosen to be 5. Alright, there is no earthly reason to choose 5. Further, there is no earthly reason to choose the same maxima for all the 3 integrators. Okay, alright. So, but in any case, you know, I mean, for example, now in this, if I wanted to make x2 max equal to say 2.5, what should I do? I want to keep x1 max and x3 max the same. If I wanted to make x2 max 2.5, what would I do? I will multiply this by half, so I will make it 1/2 into what it was earlier. Alright, and what should I do? What else should I do? I should multiply, make this 2k2 and two times 5/7. Does it make sense? Alright. So this procedure is called dynamic range scaling or node scaling. Is this clear?
So in general, you try to make this X as the noise of the op amp, right? Like you're using generally the same op amp for all the three.
No, it depends, right? Some of, I mean, you could, for example, use different op amps because the thermal noise requirements on, I have not covered it here, but the thermal noise requirements on the first integrator are the most stringent, whereas these can be much noisier. So I would use cheap low power op amps for these two guys and use a solid op amp for this chap. The swing here is the most important, right? Whereas here swing is not that important. So you know, in principle, you would definitely use at least 2 types of op amps. One for these two guys and one for this guy. Pardon? Oh, well, see, this op amp will swing the largest, correct? Whereas the noise of requirements of these two integrators is very less. For those of you who don't understand noise, never mind. The noise requirements of these two guys are very less. So in other words, the impedance levels of the R used for these integrators can be much larger. The power burnt in these op amps can be much smaller. Whereas this has to be very low noise and high speed, because this is, you know, basically handling a lot of high frequency components, because most of the high frequency, the shape noise is at high frequency. This guy handles, you know, whatever, it's looking at filtered noise. So that, you know, and whereas this guy is handling filtered noise which has been filtered twice. So the speed requirements of this op amp are much lower. Okay, so if you want to optimize, you know, power, you make this the best, these two cheap. Alright, so for those of you, I mean, O5 BTEX, are you familiar with this state space stuff? You have done it in control, correct? Okay, so once you figure out what K1, K2 and K3 are, I don't know, this does this ring a bell? What is this called in state variable form? When I scale the coefficients, when I scale the states all by some numbers, but I still have the same what do you call, transfer function. What is this called? No? What? H infinity. What is it called? I have transformed one linear system into another, It has the same poles and same zeros. Does this ring a bell? It's called the similarity transformation. You heard of it? Eigenvalues are preserved because of the closed loop poles are the same, so the eigenvalues must be the same. Okay. In other words, the original system was of the form x dot is ax plus du, y is cx plus du. In a particular case of delta sigma modulator, the loop filter d must be 0 if there is no excess delay, because this is d is the direct path from the input to the output, so that must be 0. So, okay, if you have excess delay, there will be that to compensate it, you will have a direct path. But this is the nature of the equations. Now, you want to make sure that you want to multiply all states by. So, you want a new set of state variables such that x1 is nothing but, let me call this tx, alright. Okay. So, if you are simply scaling, you want to scale the magnitudes of the original state variables, what kind of matrix will T be? It will be a diagonal matrix, alright. So, if x1 is equal to tx, how can I write the state variable equations in terms of x1? X is nothing but T inverse x1, alright. So, T inverse x1 must be equal to A times T inverse x1 plus du, alright, and y is nothing but C times T inverse x1 x dot, sorry, alright, which basically means that x1 dot is TA T inverse plus TB times u, y is nothing but CT inverse times. Alright. So, this is in short form all that stuff that we discussed. Okay. Right. So the new A is TA T inverse, alright, and the eigenvalues are all maintained. Okay. So, this is called a similarity transformation. What we have done is found a diagonal matrix T such that the maximum values of x1 are what you want. Okay. So, all that this requires to find T is run one simulation with the original stuff that you have which are not scaled, find the maxima, and then find the by how much each variable must be scaled. So, you can find T, alright. Once you find T, you can go and find the new A by just doing T at T inverse. The B is TB, and C, the new C is C times T inverse. Does it make sense? This is in concise matrix notation, all the big Ramayana that we have discussed. Okay, so you increase this gain, reduce this gain, all that stuff is succinctly expressed in these equations. Alright, does it make sense? So, see, one aspect of continuous time delta sigma is the fact that it involves some familiarity with linear systems, some obviously with transistor level circuit design, and some with Z transforms and signal processing and this kind of stuff, which I suspect is why there is such a big barrier of entry to this thing, because it's hard enough to know one thing reasonably well, right? This demands, it doesn't require you to be an expert in any of these things. It's all basic stuff that you've learned in an undergrad level class. Okay, you should be comfortable manipulating matrices, which is, I think, a lot to ask people after their undergrad. Okay, so which is one reason why the stuff is considered difficult stuff. Okay. So let me give you a quick demo of this stuff. Okay, so how one would go about designing a continuous time sigma delta modulator. This is a MATLAB script which extensively uses the sigma delta toolbox. Okay, I draw your attention to these statements. Are you able to see the print at the back? What is? Can you read this, Sandeep? All right. Okay. So I'm trying to design a third order modulator with an oversampling ratio of 64, an out of band gain of 3, a 16 level quantizer, and a signal bandwidth of 25 kilohertz. So the sampling frequency is nothing but the oversampling ratio times twice the signal bandwidth. All right. And TS is 1 over Fs. Okay. This is the sampling period of the modulator. So the next job is to oh god, I don't know why it's taking so long.